So as you saw in that scene, the ship was moving forward when it shot the shell, and according to Newton's law of inertia, an object in motion will stay in motion unless acted upon by an outside force. And therefore, since the ship was moving forward when the shell was shot, the shell should already have a forward trajectory. Now, looking at the outside forces that will affect the trajectory of the shell, we figured out that the wind speed is 23.3 kilometers per hour by searching up average wind speeds in Kauai, Hawaii, where the shot was filmed. And the wind was also blowing towards the shore, which is the same direction as where the shell was shot. Now, we had to calculate air resistance because it is a force that will be affecting the shell in the opposite direction, and we calculate that by multiplying air density times drag coefficient times the area of the projectile and dividing all that by 2 times the wind speed squared. The area of the projectile was calculated by multiplying 2 pi times 5.08 centimeters, which is the diameter of the shell, times 5.08 plus 44, which is the length of the shell, all coming out to 1,566.6 centimeters squared. The air density we figured out was 1.225 kilograms per meter cubed at sea level, and the drag coefficient of air is 0.05. Multiplying all those up, we figured out the air resistance should be 0.088 newtons. And we also have to realize that gravity exists, which is the whole reason why the shell actually comes back to the water.
So the air resistance only matters because it will drag on the shell and shorten the trajectory so that it's more likely to hit the ship. The shell's slowdown that we can calculate with that air resistance, we can use Newton's third law to calculate with force equals mass times acceleration rearranged to acceleration equals force over mass. We use the mass of the shell, which is 7.71 kilograms, to calculate this with our nice formula and find this really tiny acceleration. It's negative here because it is pushing against the direction the shell is trying to go. Now, if we take our time that the shell was in the air, which we got from the scene, and use our definition of acceleration formula, we can find our change in velocity by multiplying acceleration times the time. Right here, we have negative 0.613 meters per second slowdown for the shell, which is pretty much minuscule. And this just says the negative is the opposite of the shell's motion, which is towards the boat.
Regarding air resistance, we know that it has such a minuscule effect on the shell speed, and estimating the boat speed to be about 4.7 meters per second, we have such a small margin of error in our calculations because air resistance is so small, so we're going to kind of roll with the shell speed also being about 4.7 meters per second. And now, in the scene, we notice that the ship stopped for about 1.5 seconds. And it seemed to happen abruptly. And if it did happen abruptly, we could estimate the shell to still land about 7.1 meters ahead of the ship. But because ships cannot stop instantly, we know that it has to slow down. And because of that, best case scenario, the ship is probably slowing down for about 6 seconds. And with a gradual slowdown, we're going to use half of the initial speed to bring that out to 2.4 meters per second. And with that in mind, we can imagine that the ship will probably travel about 14 meters if it's slowing down gradually. And plugging numbers back in for the time and the speed of the shell, subtracting that 14 meters from it, we could estimate that the maximum distance that the shell probably traveled ahead of the ship is 21 meters, which is more realistic. And if you're looking at the minimum of 7.1 meters and the maximum of 21 meters, it would more than likely be much closer to the 21 meters because ships cannot stop abruptly. They have to slow down.
In conclusion, we decided that the scene could not happen in the realm of real physics. We determined that the shell would miss the ship because the ship stopped, so the shell would just continue to move forward with inertia. This is probably because they decided to film the ship stationary for the explosion. So the idea for the stunt is valid in the realm of real physics, and it could be possible if they would have just filmed the ship moving in the end.